the CAN messages. CAN uses short messages. The maximum utility load is 94 bits. There is no explicit address in the messages. Instead, the messages can be said to be contents addressed. That is, their contents implicitly determine their address. There are 4 different message types, or frames, on a CAN bus. 1, the data frame. 2, the remote frame. 3, the error frame. And 4, the overload frame. The data frame. Summary. Hello everyone, here's some data labeled X. Hope you like it. The data frame is the most common message type. It comprises the following major parts. A few details are omitted for the sake of brevity. The arbitration field, which determines the priority of the message when 2 or more nodes are contending for the bus. The arbitration field contains, for CAN 2.0a, an 11-bit identifier, and 1 bit, the RTR bit, which is dominant for data frames. For CAN 2.0b, a 29-bit identifier, which also contains 2 recessive bits, SRR and IDE, and the RTR bit. The data field, which contains 0 to 8 bytes of data. The CRC field, which contains a 15-bit checksum calculated on most parts of the message. This checksum is used for error detection. An acknowledgement slot. Any CAN controller that has been able to correctly receive the message sends an acknowledgement bit at the end of each message. The transmitter checks for the presence of the acknowledgement bit and retransmits the message if no acknowledge was detected. It is worth noting that the presence of an acknowledgement bit on the bus does not mean that any of the intended addressees has received the message. The only thing we know is that 1 or more nodes in the bus has received it correctly. The identifier in the arbitration field is not, despite of its name, necessarily identifying the contents of the message. The remote frame. Summary. Hello everyone, can somebody please produce the data labeled X? The remote frame is just like the data frame with 2 important differences. It is explicitly marked as a remote frame, the RTR bit in the arbitration field is recessive, and there is no data field. The intended purpose of the remote frame is to solicit the transmission of the corresponding data frame. If, say, node A transmits a remote frame with the arbitration field set to 234, then node B, if properly initialized, might respond with a data frame with the arbitration field also set to 234. Remote frames can be used to implement a type of request-response type of bus traffic management. In practice, however, the remote frame is little used. It is also worth noting that the CAN standard does not prescribe the behavior outlined here. Most CAN controllers can be programmed either to automatically respond to a remote frame or to notify the local CPU instead. There's one catch with the remote frame. The data length code must be set to the length of the expected response message, otherwise the arbitration will not work. Sometimes it is claimed that the node responding to the remote frame is starting its transmission as soon as the identifier is recognized, thereby filling up the empty remote frame. This is not the case. The error frame. Summary. Everyone aloud. Oh dear, let's try again. Simply put, the error frame is a special message that violates the framing rules of a CAN message. It is transmitted when a node detects a fault and will cause all other nodes to detect a fault, so they will send error frames too. The transmitter will then automatically try to retransmit the message. There is an elaborate scheme of error counters that ensures that a node can't destroy the bus traffic by repeatedly transmitting error frames. The error frame consists of an error flag, which is 6 bits of the same value, thus violating the bit stuffing rule, and an error delimiter, which is 8 recessive bits. The error delimiter provides some space in which the other nodes on the bus can send their error flags when they detect the first error flag. The overload frame. Summary. I'm a very busy little 82526. Could you please wait for a moment? The overload frame is mentioned here just for completeness. It is very similar to the error frame with regard to the format, and it is transmitted by a node that becomes too busy. The overload frame is not used very often, as today's CAN controllers are clever enough not to use it. In fact, the only controller that will generate overload frames is the now obsolete 82526. Originally, the CAN standard defined the length of the identifier in the arbitration field to 11 bits. Later on, customer demand forced an extension of the standard. The new format is often called extended CAN and allows no less than 29 bits in the identifier. To differentiate between the two frame types, a reserved bit in the control field was used. The standards are formally called 2.0A with 11-bit identifiers only, 2.0B extended version with the full 29-bit identifiers or the 11-bit, you can mix them. A 2.0B node can be either 2.0B active, i.e. it can transmit and receive extended frames, or 2.0B passive, i.e. it will silently discard received extended frames, but see below. 1.x refers to the original specifications and its revisions. New CAN controllers today are usually of the 2.0B type. A 1.x or 2.0A type controller will get very upset if it receives messages with 29 arbitration bits. A 2.0B passive type controller will tolerate them, acknowledge them if they are correct, and then discard them. A 2.0B active type controller can both transmit and receive them. Controllers implementing 2.0B and 2.0A and 1.x are compatible and may be used on the same bus as long as the controllers implementing 2.0B refrain from sending extended frames. Sometimes people advocate that standard CAN is better than extended CAN because there's more overhead in the extended CAN messages. This is not necessarily true. If you use the arbitration field for transmitting data, then extended CAN may actually have a lower overhead than standard CAN has.